All right, so the last topic of the course is implementing generic lists. So both array-based lists and linked node-based lists. When we're implementing lists, we're also going to implement iterators for the lists. So that'll let people loop over the elements of a list. Now, just to quickly remind you, a list is a finite collection of elements held in a linear sequence. Each element has an index, right, from 0 up to the size of the list minus 1. You've seen the list interface, and you've seen the array list class, right? So you know that the standard library already has the list, array list class. It also has a linked list class. But it's useful to know how these things are actually implemented. Although I think you may have already seen them in your previous course. All right, so we have so we're going to implement a simplified version of the list. So we're not going to implement the full version of Java's list interface. We're going to pick some of the more important methods, and then I'll show you how you implement these in the two different kinds of lists. So we've got size and is empty, right? Size, number of elements in the list, is empty, is the list empty, right? Get and set, so get and set an element of the list by index. Add adds to the end of the list. Now the other version of add really should have been called insert, because that's really what it is. So the second version inserts an element somewhere in the list, right? Possibly having to move other elements of the list. Remove removes an element by index. And then finally, the iterator method is the method that returns an iterator that lets people who are using the list loop over the elements of the list. So creating the interface is straightforward, right? It looks the same as any other interface that we've created. What are the notable things here? I guess the fact that it's a generic interface, right? So it's generic on the element type E. Now the odd thing is when you implement an interface in another interface, it's not the keyword implements. It's not the keyword implements, it's the keyword extends. So the list interface extends the iterable interface. And which means we need to provide an iterator method in our interface as well. There's nothing else to talk about in the rest of the interface. It's just the list of methods. When we go to implement our first type of list, though, we have to implement that interface there. So in an array-based generic list, we're going to use an array to store the elements. Now, all the issues that we had before when we made an array-based stack and an array-based queue, we have the same problems when we implement the array-based list. Right, sometimes we have to expand the capacity of the list, and it turns out there's some extra issues here. We're going to have to move elements around in the list, which complicates things. Right, so inserting an element into the list and removing an element from the list requires a very small amount of explanation. Right, so if you want to insert an element into the list via an index, that's the second add method. Right, so if you wanted to add into this list at element 4, and the list already has 9 elements in it. And then the way the method works is it has to move a bunch of elements over to the right to make room for the element that we're going to insert here. Right? So in other words, we don't just overwrite the element that's sitting at the 4, at index 4. We have to move everything over to make room for the new element. Right? So in other words, I have to take all the elements starting at the index, right, going to the end of the list, and we have to move them over one position to the right. Right? So we have to do that. Right? And that frees up a space at index 4 where we want to insert the new element. Right? Once we've got that free space, we can now add the element to the list at index 4. And that's straightforward, right? You just set the element at that given array index. Now the other odd thing about this method is that you're allowed to insert at the end of the list. Right? So you're allowed to use the index 10 in this method. Now 10 is not a valid index for this list. Right? So the valid indexes for this list are 0 through 9. Right? 10 is the next element, right, in the list. So that's technically not a valid index. However, this method allows you to set that element. Right? So if you add at index 10, that just adds to the end of the list. Right? And that's slightly unusual because that index is technically not valid. But adding at the end of the list is straightforward, right? If you detect that you have to add at the end of the list, just call add, right? The other version of add, which adds to the end of the list. So we can easily check for this case here. If you want to remove an index from a list, well, this also involves shifting elements around in the list. So if I want to remove the element at index 4, then what I need to do is, so number one, we have to, normally the way remove works is you return the element that's removed. So I have to remember what element is there now. Then I have to take all the elements after index 4, right, the ones in red, and I'm going to move them over one position to the left, right? And so that removes, right, that effectively overwrites or removes the element that was at index 4. Right? And the element at index 10, we have to get rid of somehow. Oops, okay. So that moves us into the next deck of slides. All right, so when you look at those previous illustrations, it should be clear that adding into the middle of the list or removing from somewhere in the middle of the list, the complexity of those operations is in ON, right? Because you have to potentially move all but one of the elements in the list, right? So that's, you have to move up to n minus 1 elements, right? Now, because that value depends on n, we're in ON. All right, so to implement the list, it's relatively straightforward. It looks the same as a stack or a queue. So you have an array to store the elements, right? Its type is object because you can use an array of objects to store any element. Right? We keep track of the size, and we have a default capacity, right? So this is just the starting size of the array. Right? So the no argument constructor makes the new array, sets the size to 0. Right? The size method just returns this dot size. Add adds to the end of the list. So this is like pushing an element onto the top of a stack. Right? So number one, check if you have to resize the array, right? Because we're going to try to add an element to the list. So if the size of the list is equal to the capacity of the array, we have to resize the current array, right? And we just use arrays copy of to do the resizing. Right? Make sure you multiply the length or the capacity of the array by some factor times the current capacity of the array. Right? And then just go ahead and set the element at this dot size, right? And then increase the size of the list by 1. So that's the exact same as pushing an element onto a stack. A lot of the methods in the list class are most of them are index-based. And so it's nice if you check whether or not the index that's used by the caller is valid, and if it's not, throw an exception. So I've got a little method here. It's private. Its only job is to check the index that's passed into it. Right? So if this index is less than 0, it throws an exception. If it's greater than or equal to the size, it also throws an exception. Right? And it produces an informative error message in both cases. Right? If it's a negative index, then it tells you you used a negative index. Right? And if the index is too large, it tells you that the index is too large. Right? The standard exception that you throw in this case is something called index out of bounds. Get and set are straightforward. Right? So if I want to get an index, I know where it's stored. I know where the element's stored in the array. Right? It's just stored at that index. So I just go to that index in the array and return that element. Right? You need the cast because the return type here is E. Right? The type of this array is an array of object. So I have to convert object to type E before returning it. Check the index using our method. Right? Set is also straightforward. Right? I'm going to use get to get the old index. Right? Now there's a reason for doing this. Right? The reason for using get is because get checks the index already. So I don't have to check the index here myself, although you could. There's no reason you couldn't. Right? So check the index and then just go ahead and get the element at that index. Right? Once you've got the old element, simply overwrite the element with the new element and then return the old element. Right? So all those methods are straightforward except when you get to add or you insert into the list. So it's a little bit tricky to implement this thing, especially if you don't have any unit tests. So when you go if you were asked to implement this thing, the very first thing you should do is to write a bunch of unit tests because you're almost certainly, even though it's conceptually simple, you're almost certain to screw it up. So number one, we have to validate the index, but remember this version of add, the index is allowed to be equal to the size of the list. Right? That doesn't work for our check index method. Because our check index method, if you pass in the size of the list, it throws an exception. So I can't check the index using our method right here. So instead, what we have to do is we have to look for the special case where the index is equal to the size of the list. Right? So if it's equal to the size of the list, the caller is telling us they want to add the element to the end of the list. Right? The other version of add already does that for us. So we simply call add and add to the end of the list and then return. Right? If you forget that return statement, then you end up adding the element twice. So that's the first easy mistake to make. Right? Second, then the next thing to do, now you can check the index. Right? So now that I know that it's not the special case, right, I can check the index using our checkIndex method, right, and that will throw the exception if the index is not somewhere in the actual list. Right? Assuming we get past this line here, we now have to do the shuffle. Right? So I have to make room for the element by moving a bunch of elements to the right. So how do you do that? Well, you start. So I want to move the elements at indexes size -1. Right? So the last element. Right? Size -2, so the second last element. Size -3, the third last element, and so on. Right? Down to the element sitting at the given index. Right? And I want to move those over one position to the right. Okay? So the way to do this is to start at the end of the list. Right? This is the other easy mistake to make. Right? You start at the index and count up. So if you do that, then you move the element at index one position to the right, but that overwrites the element that's sitting one position to the right. Right? So if you do it that way, you have to take care to remember what the element is sitting to the right. So it's easier to start at the end of the list. Right? Now the index I here that I'm using, so you need two indexes. Right? You need the destination index. Right? So where am I going to write into? And you need the source index, right? Where am I copying from? Right? You have to make sure that the destination and source indexes are both valid, right? Otherwise, if they're not, this will throw an exception. Right? So you have to be very careful when you write this loop. Right? So I'm going to start at size -1. So in other words, I is going to be my destination index. My source index. Right? So I'm going to start at the end of the list. I'm going to count down, right, to the value index. So the next element in the list, right? So the next element to the right of I is equal to the element at index I, right? So that effectively shuffles all the elements that you have to move one position to the right, and that opens up a spot to add the element. Right? Once that loop is done, go ahead and set the element at that index, and then increase the size of the list by 1. Right? So it's not exactly trivial. It's not super hard to write, but it's not that easy to write either. It's very easy to screw this up. And in fact, there is an error on this slide, and I'll let you figure out what the error is. It's not so much an error, there's an omission. Right. Okay, now what about remove? So remove, I have to move elements over to the left. Right? So the way that you write your loop is different. So I'm going to remove also removes the removed element. So if I use get, that validates the index for me. Right? So I don't have to bother doing the validation if I use get. So the removed value is just going to be the current value sitting at the at that index. Right? Now I just move elements over one to the left. Right? And so the way you write this loop is you write it the other way around. Right? So now I start at the element index +1. And I move it over one position to the left. Right? So if I is my index, then the position to the left is just I -1. Right? The element that I move is just the element to the right, so that's just the element at index I. Right? When you write that thing right there, right, you have to make sure that I -1 and I are both valid indexes. Right? So I is definitely a valid index, right, because index is a valid index, and this dot size -1 is a valid index. So that's not the problem. The question is can this ever be negative? Right? And the answer is no, right? Because index is valid. So the smallest value for index is 0, right? I plus 1, so 0 plus 1 is 1, 1 minus 1 is 0. So that's never going to throw an exception either. So you know that, so you can be pretty confident this is correct. If you're not confident this is correct, at least it won't throw an exception. Finally, you can set the element at the last element, the old last element that was in the list. Right? We null that out. Right? The reason we null it out is so that you remove the reference from the list, and that lets the garbage collector remove that object from memory if the user doesn't need it anymore. Then you decrease the size of the list, and then you return the removed element. Right? So this, both of these operations are common when you have to work with array-based structures, where you can add or remove somewhere into the middle of the array. Right? And so in other words, whenever you have to add or remove from the middle of an array, you have to shift elements around. Okay. Any questions so far? Yes?
What's the reason to implement the list with an array as opposed to just like a regular linked list with like a pointer and you're adding, I don't know, because in C we were mallocking every time we added a new
Yeah.
What's the reason to like block off a chunk of memory with an array and do it that way?
So what's the complexity of so if you want to add an element to the end of a list, right? So what's the complexity for adding to the end of an array-based list? O1 most of the time, On some of the time, right? Because sometimes you have to reallocate the underlying array, right? Okay, so what about getting an element from an array-based list?
O1.
Yeah, and setting an element in an array-based list?
It depends from where. But I mean, don't you have to shuffle back?
Not to set. To insert, yes, but not to set.
Okay, O1.
Right. So what about get in a linked list? It's always On. What about set in a linked list? Always On. Get and set are the most common operations that you perform on a list most of the time. So a linked list is going to be much slower. Right? If you search for an element in a linked list and you do it naively, so the naive implementation of search in a linked list is you use get, right? So you write a loop, I equals 0 up to the size of the list minus 1, and then call get every time. Your search method becomes On squared.
Right.
Because every time you call get, you pay a price of On. So it's very easy to write bad linked list methods. Right? So linked lists are generally slower. There's almost no use case for a linked list in any programming language. Right? Even in C, you would normally use a straight array. Yeah. The use cases for a linked list are extremely rare. Yeah, so the reason they taught you that, though, is to get you used to pointers. Right. Yeah. Also, if you have a small linked lists are fine. Right? If you have like a small list you never worry about, then you don't care how the list is implemented. Right? In that case, it's often convenient to use a linked list, especially if you're going to do something like a stack or a queue. So if you implement a stack or a queue using a linked list type structure, those can be very fast. If it's small, then you don't care that you have to follow a few links every time. So a lot of the time, C programmers will just whip up a quick linked list because it's easy to do, right? But if you really need a list, then normally you would use an array-based list. Yeah. In Java, you almost always pick array-based list. Okay, so the iterator method. So to implement the iterator method, we need an iterator class, right? Now remember what iterators do, they're just objects that know how to loop over a sequence, right? So we've seen one iterator so far, right? But this was a couple of weeks ago. So we implemented an iterator when we did that range class. We now need an iterator that loops over an array-based list, right? So because our interface, it's not on the slide. Sorry. Because our interface back here. Our interface says it implements the iterator method. So any class that implements our list interface also has to provide the iterator method. Right? So to provide an iterator, we're going to create a private class, an inner class, that implements an iterator. Right? And so our iterator method simply returns a new one of these. Right? Now the class is private, so no one else can make an array iterator directly, which is fine because you wouldn't normally do that anyway, right? You would just call the iterator method. Number two, this is not a static class, right? So remember, there's two types of inner classes, right? There are static inner classes, and then there is regular inner classes. This is a regular inner class, right? So a regular inner class, our iterator object has a reference back to the list object that made it, right? In static inner class, that's not the case, right? So our iterator knows which list it's iterating over. That makes sense, right? The iterator needs to know what list it's iterating over. So that's why it's not a static inner class. The iterator implements the iterator interface, right? So we should, is it here? Oh, okay, so I'm now going to review that interface because it's been a while since we've seen it, right? It's been about 10 lectures since we've seen that interface. So an iterator is just an object that knows how to loop over a collection or a sequence of values. Now it turns out that the only safe way to loop over a list and remove stuff from the list or set, right, is to use an iterator object. Right? So in other words, you create an iterator object, use the iterator to loop over the sequence. Right? Every time you look at an element, if you want to remove it, you ask the iterator to remove the element for you. Right? You don't ask the underlying sequence to remove the element. Right? So this is the only technically safe way to do this. If you're extremely careful, you can do it with a regular loop in a list, but you have to be very careful and you have to really understand what remove is doing every time. So if you look in those notebooks, they actually show you how to use an iterator to what's called filter a list or a set. Right? So anytime you write a for each loop, you're actually using an iterator object. Right? So it's actually fairly important if you're going to implement a collection that you provide an iterator for the users. The iterator interface has two methods that we have to implement. Right? So you have to implement hasNext, and that just returns true if there's another element in the sequence for the iterator to visit. Right? Next gets the next element in the sequence for the iterator to visit. If you want to remove elements from the collection, then you have to provide a remove method as well. Right? So this is actually a default method in the interface, right? And the default method just throws an exception when you call it. Right? So in other words, this is the way that you can provide what's called an optional method in Java. Right? In the interface, create a default method, right? That provides an implementation of the optional method. Right? If your class doesn't want to implement it, you don't implement it. Right? Someone calls the optional method, they get an exception. Right? If your class wants to implement it, then you go ahead and override it, and you get rid of that exception. Right? There's one more default method, but it's not important for our purposes. Okay, so to implement remove, you have to know what remove does. Right? So remove removes the element that was most recently returned by next. Right? So it's a bit odd that, on how you use iterators. Right? So the way you use an iterator is you normally call hasNext to see if there is a next element. Right? If hasNext is true, you call next. That gives you back an element. Right? And then if you want to remove that element, then you can call remove. Right? But you can only call remove if you've already called next. You can only call remove once every time you call next. Right? So you go to the next element, remove it or not, it's up to you. Right? Go to the next element, you can remove that one or not, it's up to you, and so on and so on and so forth. Right? But you can't remove two elements in a row. Right? So you can't call next and say remove, remove. Okay, so when you loop over a sequence and remove elements based on the value of an element, that's called filtering a collection. Right? So for example, if you want to remove all the negative values from a list or set, you can write the following method. Right? Not method, you can write the following code. Right? So I've got a list or set T. Right? You create an iterator over the set or list, right? Just by calling the iterator method. Right? The loop continues to run as long as the iterator has another element to visit. Right? So that's where you use hasNext. There's no update. There's no update expression in this loop. Right? So it's a bit of a funny loop to write. Right? There's no update expression here because you're going to call next. Right? And next advances the iterator each time. Right? So inside the loop you call next, and then you look at the next returns the next element in the sequence. Right? You now can look at the value. If the value is less than 0, you can remove it. You remove it using the iterator. right? So you don't remove it using t's remove method, right? So use iter remove to remove the element, right? And the iterator knows how to remove that element from the list, right? And that's why the iterator needs a reference. That's one of the reasons why the iterator needs a reference back to its list that it's iterating over, right? The only way the iterator can go into the list and remove the element is if it knows where that element is. If it knows how the inners or how the list is actually implemented. Okay, so what is an iterator? So we need to know how to implement this iterator thing. So you need a conceptual model of what an iterator actually is. Right, so if you have a regular text editor, you've normally got a cursor that blinks, right? So that blinking cursor, right? You can imagine that cursor sits between letters, right? So that cursor right there is sitting between the Y and the I. You can imagine that's an iterator, right? So our iterator here, shown in red, right, sits between the elements at indexes 7 and 8, right? So it's sitting between these two elements. The previous element is the element at index 7, right? So it's the element immediately to the left. The next element is the element at index 8, right? So it's the element immediately to the right. If you call next on this iterator, it returns the element to the right. Right? So in other words, you advance the iterator to sit between the 6 and the 10, right? And it returns the element that's 6. Right? Oops, sorry. Right. So after calling next, the iterator advances down the sequence, right? So it moves one position to the right, right? So there it is there, and now you call next, it moves one position to the right. If you reach the end, right, the iterator that's sitting at 1 past the last element in the sequence, right, that iterator has reached the end of the sequence. Right? So that iterator right there, if you call has next, will return false. Right? Remember, previous is the value 11. Next is the element null, right, which is 1 past the end of this list. Right? So that iterator there will return false for has next. Right? If you try to call next on this iterator, it'll throw an exception. Right? Because there is no element, there is no more elements left in this collection. At the start of the list, so when you make an iterator, the iterator normally starts at the front of the list. Right? So at the front of the list, there is no previous element. Right? There is a next element, but there's no previous element. Right? So we're going to set previous equal to -1. So our values previous and next, they're going to be the indexes of the previous element that was visited by the iterator and the next element visited by the iterator. Okay. So our array iterator class, basically we have to implement these pictures here. Right? We have 2 fields, right? One called next and one called previous. Right? So next is the index of the element returned by the next call to next. Right? Previous is the element is the index of the element returned by the most recent call to next. Right? If you remove an element, we're going to reset previous to -1 to indicate that we've removed an element using remove. Right? Now, the reason we're going to do this is because we don't want to call remove twice. If someone calls remove twice, we have to throw an exception. Right? So I need some way to detect that remove has been called once already. So what I'm going to do is I'm going to set previous to an invalid index. Right? By setting it to an invalid index, that's going to give me a way to detect that remove has already been called. Right? Okay, so our constructor creates an iterator that starts at the front of the list. Right? So its next field gets set to 0. Right? Why does it get set to 0? Because that's going to be the index of the element returned by the next call to next. Right? So when you call next the first time, it should return the first element in the list. So that's the element at index 0. There is no previous element, so we set it to -1. Okay, how about has next? So you know that has next returns true as long as there's something left for the iterator to visit. Right? So how do you know when it returns false? Right? So this is the picture that tells you when has next returns false. Right? Has next returns false when the iterator, when it's either its, so you look at its previous value or its next value. Right? You should probably look at the next value. Right? So the next index here is 15. Right? But that's equal to the number of elements that's in this list. So if next is greater than or equal to the size of the list, you know it should return false, right? Therefore, it should return true if next is strictly less than the size of the list, right? Now, how do you get the value of the size of the list from the list, right? So you have to remember that you're in an inner class, right? So we're inside the array iterator class, which is inside the sArrayList class, right? So if we're an inner class and we want to get access to the enclosing classes field, you use the name of the enclosing class, right? So sArrayList followed by this, right? sArrayList.this.size is the size of the enclosing ArrayList object, right? So implement has next is fairly straightforward, right? Now next is a little bit trickier, right? So next should throw an exception if there is no next element, right? How do I know if there's no next element? I just call hasNext, right? So if hasNext returns false, throw a no such element exception. That's the standard exception that iterators throw if there are no more elements in the sequence, right? And now we need to implement this picture and this picture, right? So next should return the next element in the sequence, and it should advance the iterator one position to the right. Okay, so what's the next element in the sequence? Well, it's just the element sitting at this dot next, right? So I can call the get method from the list and use pass in the index this dot next. If you want to, you can access the list, the array directly, right? So you'd also write sArrayList dot this dot arr square brackets this dot next, right? That's fine as well. Right. Oh, actually, it's right there. Slightly more efficient would be to write that, right? Why is it slightly more efficient? Because get validates the index. I already know the index is valid, right? Then what do you have to do? You have to advance the iterator one position to the right, right? So the way you do that is you increase next by 1, right? You can set this dot previous to equal the current value of next, right? Which will advance previous one position to the right, right? And then return the element E. All right, now what about remove? So remove is the tricky one. So I've got this iterator sitting right here, right? So it's sitting between the 6 and the 10, right? So remember what the most previous, the element that was last returned by the iterator was the 6, right? So in other words, it's the element that was sitting, that's sitting in previous, right? The next element that should be returned, right, when we call next again is the 10, right? So we want to remove the 6, right? And we want to remember that the next element is 10, right? So we want to remove the element at index 8 and remember that the next element to be returned is the element sitting at the old index 9. Now remember what happens when I remove that 6, right? All these elements are going to go over one position to the left, right? Do I have a picture of that? I do, okay, right? So I remove the 6, and now this is the picture of my list, right? The iterator hasn't moved yet, right? But notice what's happened now. Previous is now 10, right? Which is supposed to be the new next, right? It's not supposed to be the old, it's not supposed to be the current previous, right? So I have to back the iterator up one position when you remove, right? Okay, so I want to remove that 6. I want to remember that I have to return that 10, right? So I'm going to remove the element at index previous, right? How am I going to do that? I'm just going to use the ArrayList method remove to remove that element, right? After removing the 6, we're in this situation here, right? The iterator is now one position too far to the right, right? So next has the wrong, next is now has the wrong index, right? Next is now next is always was 9, but that's going to return the 4, and I need to remember that it's the 10 that I'm supposed to return, right? So to fix this, you just decrement the next. So I take 1 away from next and move the iterator back one position, right? And now finally, right, so previous and next now both point to the same element, right? I want to set previous to -1 to indicate that we can no longer call remove, right? So I want to set previous there and make it point, whoops, sorry. Previous should now point to the element that's 1 in front of the first element. Okay. So once you've drawn these pictures and figured out exactly how this works, right? The easy thing to forget is that once you remove that 6, everything moves over one position to the left. Right? So it's easy to forget to update this iterator, moving it backwards one position. Right? So to implement remove, right, we should throw an exception if someone's already called remove once before, since calling next. Right? We also want to throw an exception if there is no element to remove. Right? So there's no element to remove if the iterator is sitting at the front of the list. Right? In both cases, right, you can detect that situation by looking at the value of previous. Right? So if previous is -1, I know that there's no element to remove, or we've already removed an element. Right? If you detect that case, you should throw what's called an illegal state exception. So if you read the documentation for the iterator class, that's the exception that you throw. Yeah?
What's wrong with removing something twice in a row?
The iterator can't do it. That's the problem. So you can probably implement an array list iterator to do it. Right? So an array list iterator, you can probably create an iterator class that will do it correctly. You can't do it for a linked list easily. That's the problem. And you need the iterator interface to work for all, quote unquote, all kinds of lists. It actually depends on what type of linked list you have. For a singly linked list, there's no good way to do it. There's no good efficient way to do it. For a doubly linked list, you could do it. Okay, so if I can remove an element, we just remove the element using the remove method from the list class. Right? So remove the element at this dot previous. Right? Decrement the next value by 1 to move the iterator back one position. Set previous to -1 to indicate that we've removed an element and there's no more, and I can't do it again unless we call next. Right? If you go back and look at next, right, that's why next was implemented the way it was. Right? So in next, you might think that to update previous, you just add 1 to the current value of previous. Right? So in other words, you might think I can just write this previous plus plus, right? Because I can do that with next, right? But instead, we write this previous equals this dot next. Right? Now the reason we do that is because, right, if you remove an element, we set previous to -1, right? If you implement next by saying this previous plus plus, right, previous becomes 0 instead of being equal to the old value of this dot next, right? So that's a subtle, that's a very subtle implementation detail of the next method here, right? That's easy to screw up, right? It's very tempting to write this previous plus plus, right? But if you do that, as soon as someone calls remove, your next method breaks. Right? So there's a lot of subtlety involved in implementing these iterators. This is also the reason why you shouldn't write your own collections in general. Right? The people who have written these classes have already gone through a lot of effort to make sure that they're efficient and correct. Right? It's useful going through this exercise to see how they've done it, right, and to get better at programming. But in general, you would not roll your own array list class. Right? You would just use the one in the standard library. All right. Now, if you were actually a computing science student, these lectures are probably a little more useful for you because they haven't taken the data structures course yet. Right? And so they're going to have to go through all of this in some other programming language. Let's see. Do I want to do this? I guess we can start this slide, the next part. Okay, anybody have any questions about array-based lists? So actually, everything that I've told you in the last, I guess, 40 minutes lets you implement a fully functional array-based list. Right? It almost provides all of the methods in the Java standard library array list class. Right? There's just you only have to implement a few other methods. Okay, now what about linked lists? So a linked list is the list that you've studied already in your previous data structures course, right? So you know that there's, did you do a singly linked list or a doubly linked list? Both, okay, good. So the Java standard library implementation is a doubly linked list. The one that I'm going to talk about is a singly linked list, right? So I'm not sure how they showed you to implement this thing. And I'm not sure what methods or what functions they had you write on these things. Did they show you, like, did they do insert and remove and all that stuff? Yes? Yeah? Okay. So we're gonna, I guess we're gonna do that again. But the important part is actually we're gonna implement an iterator over this thing. Okay, so I think most of this is going to be review for you then, right? So you know that in a linked list, you're going to use a sequence of nodes to store the elements, right? The first node is traditionally called the head node. The last node is traditionally called the tail node. Sometimes first and last are also used, but I'm going to use head and tail. In a singly linked list, each node has a link to the next node, and then, you know, in a doubly linked list, every node has a reference or has a pointer to the next and the previous node. Right? Now, these things look a lot like stacks or queues that are implemented with nodes. Right? So there's an example of a linked list of length 3. Right? The head node at the front, tail node at the back. Right? In Java, you indicate that you're at the end of the list by setting the next link to null. Right? The empty list has the head and the tail both equal to null. Right? Linked lists are recursive in structure, right? Just like queues and stacks. Right? So you can think of every node in this list as being the head of some other list. Do I actually have a picture of that? Yes, I do. Okay. Right? So if you wanted to implement the sublist method that's inside the list class, the list interface, this makes it very easy for linked lists. Right? So remember what sublist does. Sublist returns the part of the list that returns a sublist, right? A part of another list. So the second node, right? That's the head of a linked list of size 3. Right? The third node is the head of node of a list of size 2. And that last node is also the head node of a list of size 1. Right? Now, because the structure of a linked list is recursive, most of the list length algorithms can be implemented recursively. Right? So if you wanted to compute the size of a linked list recursively, pretty easy to do. Right? So to find the size of a linked list, right? You can make a recursive helper method called recursive size. Whoops, sorry. Right? Recursive size takes in a reference to a head node. Right? Now remember how this thing works. Right? Every node is a head node. Right? That's the head node of a list of size 4, size 3, size 2, size 1. Right? So to write your recursive helper method, right? If the head node is null, right, then you know that your list has size 0. Right? So the recursively computed size of the list is just 0. Right? Otherwise, you just keep on following the next link and adding 1 to the size. Right? So every time I follow a link, I add 1 to the size of the list. Right? So I'm going to return 1 plus, call the method recursively, passing in the next node in the sequence. Right? And that method there will recursively compute the size of a linked list. And similarly, you can write almost any other. You can use recursion to implement most of the linked list methods that we're going to implement in our interface. Yeah, I think I'll just leave it at that. Okay, so I guess that's a good place to stop. We'll look at the implementation of the linked list in the next class, including its iterator. If we get through that, I don't know if we're going to get through that. What's in the last? If we get through that, that's actually the end of the course, I think. There's no other content. Sorry, just give me a second here while I look at this. Oh yeah, okay. So the very last topic in the course is an iterator for a linked list. If we get through this on the next class, there will not be a class on Thursday. Okay? Thursday? Yeah, Thursday. All right. Any questions? All right, thanks. Have a good rest of the day. I'll see you on Wednesday.